Have you ever seen the pods that astronauts return from space in? You know, the ones that splash down into the water? They actually have a really challenging job of returning the astronauts safely from a really high potential energy situation. When they're way above the Earth, they have really high potential energy because remember that potential energy is proportional to height. So the higher you are, the more potential energy, and it's hard to get much higher than the astronauts. And as that pod craters back towards the Earth, that potential energy is converted first into kinetic energy and then into thermal energy as the friction with the air heats the pod up. The scientists creating these re-entry vehicles have an important job. They want to make sure the pod doesn't get too hot. How do they do that? Well, they have a trick up their sleeve. They use a material that can absorb lots of heat without its temperature rising very much. Something like that is said to have a high heat capacity. It can store a lot of thermal energy per temperature. In this lesson, we're going to learn all about heat capacity, all about how much energy things can store per unit temperature. Let's heat this lesson up. Let's get started by reviewing our lesson objectives. First, we'll introduce the concept of heat capacity. Then we'll investigate the impact of different heat capacities. And lastly, we'll calculate the energy required to warm objects. Let's start with a pot of water. We put it over a flame. After a few minutes, which will be hotter? The metal of the pot or the water in it? That's right, the metal. Eventually, the water will get hot and begin to boil, but metal is much easier to warm up. It takes less heat to warm up metal than it does water. This difference is captured by what we call heat capacity. Let's look at the heat capacity of water. The heat capacity of water is 4? Okay, well, clearly it's not just 4. We need some units here. But the units for heat capacity are complicated. We're going to build them up slowly. First of all, we'll add joules. So the heat capacity of water is 4 joules. That's how much energy we're going to have to add to warm it up. But you might well ask, how much water are we warming up with this 4 joules? 1,000,000 pounds? 1,000,000 grams? Well, just 1 gram. So the heat capacity of water is 4 joules per gram. That means if we apply 4 joules of heat, we can heat 1 gram of water. How much will we heat that 1 gram of water? Exactly 1 degree Celsius. So the heat capacity of water, with all its units there, is 4 joules of energy will heat 1 gram of water 1 degree Celsius. You can see why we built this up slowly. One more time, 4 joules of energy can warm 1 gram of water 1 degree Celsius. Compare that to the heat capacity of gold. Here we see that the heat capacity of gold is 0.1 joules per gram per degree Celsius. So all I need is just 0.1 joules to heat 1 gram of gold 1 degree Celsius. You can see that gold takes much less energy to warm up. It takes 0.1 joules of energy to warm 1 gram of gold 1 degree Celsius. Here's a table of a bunch of substances and their heat capacity. Pop quiz, what's the most challenging to warm? What takes the most energy to warm? Well, it's water. As we go down this list, the heat capacities get bigger, and that means it takes more energy to warm them. Substances with higher heat capacities take more energy to warm. We can actually calculate how much heat it takes to warm something with this equation. Q is the energy required, and that's going to be in joules, where M is the mass of the object we're warming, and that's going to be measured in grams. The delta T thing here is the temperature change. Remember, whenever we see that triangle, it's the Greek letter delta and it means change. And we're going to have that temperature change be in the units of Celsius. Lastly, we have this CS thing. That's the specific heat capacity we've been talking about. And it's in joules per gram per degree Celsius. So that's just a measure of how hard the substance is to warm up. Specifically, the specific heat capacity is the energy required to heat 1 gram 1 degree Celsius. And that's what we've been talking about this whole time. Let's actually put this equation into practice. This problem says a bar of iron with a mass of 755 grams is warmed from room temperature, which is 22 degrees Celsius, to 525 degrees Celsius, where it begins to glow red hot. Iron has a heat capacity of 0.45 joules per gram per degree Celsius. How much energy did the iron absorb during this temperature change? Well, let's just take a look at a picture of this process. Here we have a bar of iron sitting down in some hot coals. Initially, that bar of iron was just black. It wasn't glowing at all, and it was at room temperature, and we want to know how much heat did it absorb to begin to glow. All right, with all that in mind, let's go ahead and go through our typical procedure, where we write down the variables given. First, we're given the mass of this iron bar, which we're told is 955 grams. Then we're told that it starts out at room temperature and is warmed to 525. So we actually have two temperatures here. So it started at 22 and ended at 525. For that reason, we'll call the temperature initial, the starting temperature, 22 degrees Celsius. And we'll call the temperature final, where it ended up, 525 degrees Celsius. Okay, what other information is given? We're also given the heat capacity of our iron, which is 0.45, and then we have our mess of units, joules per gram per degree Celsius. Now, what's the variable we use for heat capacity? Do you remember? It's the CS. Okay. Now, let's recall our heat capacity equation. It's Q equals CS times M times delta T. You'll notice, though, we don't actually have delta T. We have two temperatures. So we have to calculate the change in temperature before we can use our equation. The little triangle there is always the Greek letter delta, always means change, and we can always figure out change if we do final minus initial. Just remember, that's the standard way to always find a change, is final minus initial. And so in this case, we're going to do our 525, which is our final temperature, minus our initial temperature of 22 degrees Celsius. That means our temperature change is 503 degrees Celsius. Okay, now that we've calculated our temperature change by doing final minus initial, we can use our heat capacity equation. This equation is not really new, but do keep in mind that you will need to calculate the change in temperature pretty often in these problems. So you may just want to take a special note of that. Whenever we have a change, we do final minus initial. Okay, on to calculating the energy required to warm up this iron. Well, we've already solved for Q, which is nice. So all we have to do is plug in our heat capacity, which is 0.45, times our mass, which we know is 955, times our change in temperature, which we just calculated to be 503. So we're going to multiply 0.45 times 955 times 503, which gives us a pretty big number, a lot of joules, 216,164. There's some additional digits, but we'll be rounding them off anyway. So how many digits should we round to? Well, our temperature there, 22 degrees Celsius, just has 2 sig figs, as does our heat capacity. So we'll keep the first 2, and that 6 is going to make the 1 round up, and so we'll get for our Q 220, and then we'll add the rest of our placeholding zeros. 220,000 is approximately how many joules it's going to take to warm up that iron bar. So quite a large number of joules to get that bar from room temperature to that glowing red hot temperature. Okay, now it's your turn. A pot of water with a mass of 820 grams is warmed from room temperature, 22 degrees Celsius, to its boiling point at 100 degrees Celsius. Given that water has a specific heat capacity of 4.18 joules per gram degree Celsius, how much heat was required? Pause the video and see if you can calculate the heat required. All right, here's the answer. We need to solve for Q. We know the heat capacity, we know the mass, and we can calculate the temperature change, which remember is always the final temperature minus the initial temperature. Turns out the temperature change was 78 degrees. When we calculate Q and round for 2 sig figs, we should get 270,000 joules. If you didn't get that, pause the video and just give it another try. Let's review what we've learned. First, we introduced the concept of heat capacity, where we saw that it's the amount of heat required to warm something up. Then we investigated the impact of different heat capacities. We saw that some things are much more easily warmed up than others. Lastly, we calculated the energy required to warm objects. We put our equation for heat capacity to use. Hey, hey.